Hello everybody, we are live, and welcome to Space Engine. I'm gonna grab the channel link real quick just so I could drop it in the Discord and let people know that we're live, and then we will go ahead and get started, I think. But this game is really cool, so I hope you all enjoy today. Let me just make sure that I can like properly hear myself or whatever. Gonna just check the stream settings real quick before we get started. Let's do that. It's a little bit of a process to get the stream started. See how the settings look. I think the volume's a little bit loud. I'm gonna turn the game volume, the music, using the game down just a little bit. Hello Magnus, how you doing? We're gonna be playing some Space Engine today. How do you feel about Lemon's return? Absolutely goated. Here, hold. Let me inform my Discord. Let's add everyone. Let's drop a link. We are live. Perfect. All right. So we'll see if anyone joins today, but if not, no real worries. I'm honestly just gonna enjoy flying around and exploring this game because Space Engine is really cool. The gist of this game is that also, why can I not turn right now? Hold on. Wait, this is mildly cooked. Why am I locked on Earth? Did I mess up the controls? Wait, this is gonna be incredibly embarrassing if I did. Controls. Do I have to hit something? How do I move around? This was fine literally 5 seconds ago. Oh, we have to It's okay. Nobody's here. Nobody's here. It's low-key fine. Cancel. Let me out of the menu. What's happening? Why is it like this? Why is it genuinely frozen? Okay, hold on. I might try a quick game refresh. Oh, this is really tragic. The game was working literally perfectly just a minute ago. All right. Kill the game. Stop the game. Pause the game. We have to bring it back. Oh, I'm so sorry. Okay. The game was working. The game was working fine like 5 seconds ago. Like literally 5 seconds ago. Okay, we're back, I think. Okay, let's see if that fixed it. I just did a quick game relog. Alright. And we are back. Okay, perfect. Now we can actually look around and move. Okay, perfect. So, we are currently chilling in orbit around Earth, our home planet. Now this game is super cool because looking out at these stars, by the way, there's Orion. There's the Orion constellation right there. I believe we're actually looking at it upside down from the usual perspective we see on Earth. Maybe, or I'm tweaking. Anyway, this should be Betelgeuse. Yeah, there's Betelgeuse. There's Betelgeuse. The star is actually supposed to go supernova in the relatively near future. We think Betelgeuse is destined to go supernova at some point, relatively soon. You know, we like to say on the order of magnitude with these things whenever we look at things out in space. Also, okay, C or T. There we go. Thank you. I appreciate it. For the things with the locking there. Thank you very much. How centered is this, by the way? I'm hoping we're mostly centered. Looks to be centered. This is one of my first times streaming this game, so. But anyways, I figured we'd start just around in the solar system and then venture out into the cosmos because every single one of these stars that you see in the sky is something we can go visit. So I think what we will start with here is just to get a little bit of a scale of just the size of our solar system. You know, whenever you see like a diagram of the solar system, all the planets are pretty close together usually, and they do that so you can like properly see everything. But the solar system is actually quite massive. So I'm just gonna I like to play this game without any labels on. Maybe I'll turn them on just for convenience later, so people can know what I'm looking at. But we're just gonna start out with Earth right here. We're looking at the sunny side of Earth. There's the dark side over here. You can see the sort of city lights lighting up there. But this is the light side of Earth, meaning the sun is right over there, as you'd expect. Yeah, what we're going to do is we're just going to slowly pull back. If you look at the top of my screen, velocity, that is just a percentage of the speed of light you are seeing. So we are going at 1% of the speed of light right now. So we're already going immensely fast, far faster than any object we've ever built can travel. So just to give you all a sense of scale, we are going, currently in the game, we are traveling faster than any human-made object humanity has ever made. And we're just slowly pulling back from Earth at this immense speed. 1% of the speed of light is huge. It is impossible to destroy Earth. Not this type of game. This is more of an exploratory game. Universe Sandbox you can, though. So Universe Sandbox might be a fun one to play in the future. But just to give you a sense of the size of the solar system, we are traveling at 1% of the speed of light right now. Immensely fast. Turn on orbit lines? I will. I will eventually, but for starters, we've pulled back quite a bit, and here is the moon. The moon is now in focus. So already we have this immense, we're traveling insanely fast, and we've pulled back quite a bit, and we are now only just now arriving at the moon. Let's see like what it would look like if we're traveling at the speed of the fastest thing ever, which is this Parker Solar Probe, which is currently orbiting the sun. I'm going to look up the speed of it real quick, because I'm actually not sure off the top of my head. But the Parker Solar Probe goes about 700,000 kilometers per hour. This is kilometers per second. So we're going to have to slow this way down, actually, if we want to get anywhere close to sort of the speed. This is only in meters per second. Okay, hold on. Parker Solar Probe speed, kilometers per second. 191 kilometers per second is how fast the Parker Solar Probe goes. So let's turn up our speed to that. You know what? 125 kilometers per second. That's like pretty quick. This is about right. This is about the speed. This is the speed of the fastest thing humanity has ever launched. We're quite close to the moon, so it's going to look like we're going pretty fast relative to the moon. But as you can see, if we were to travel this speed, it would take us an immense amount of time to get to Earth. Like, look how far away Earth is. It's not getting any bigger anytime soon. We can recede from the moon fairly quickly, but, you know, this is the speed of the fastest thing humanity has ever built and sent into space, and we're barely making a dent on the universal scale. This is just in between the Earth and the moon. So one of the first things I like to talk about with space is just how mind-bogglingly big it is. Like, absolutely ridiculous. Like, yeah, is there a measurement higher than the speed of light? In this game, yes. In real life, no. In real life, the speed of light is the universal speed limit. But in order to check out some things in this game, we are going to go much faster than the speed of light to even stand a chance. So, again, right now we are going at the speed of the fastest object ever created by humanity, and it doesn't look like we've gotten anywhere near to Earth from here. I could go faster, but as you can see, I just want to demonstrate, yeah, this is it. This is the fastest thing humanity has ever built, and this is what it looks like. We could fly to the Earth right now. It would take us a few days of me holding the W key at this speed to get from the moon to Earth, which just kind of makes it much more impressive that we've actually sent humans out here before to the moon, and we've actually landed on the lunar surface. By the way, let's do that real quick. Let's go in for a little landing, because in this game you actually can land on planets. So we're going to speed up a little bit just to get this landing, and we are now landed on the moon. I don't have the good textures enabled, so it's going to take a minute to load in, but there's some moon dust for you guys as we look out at the low poly landscape, because I unfortunately cannot add the best textures in or it will break my game. But there you go, that's what the Earth looks like from the moon. Some people really think the moon is a star. Yeah, it's kind of unfortunate how poorly educated people are about things in space in general. So, yeah, I think the next logical step to do is to show you what this game looks like at the speed of light. People probably are interested in this, so let's crank up all the way to the speed of light. It's being a little bit difficult here. We can go 1.5 times the speed of light. So even at the speed of light, it's going to take us, excuse me, I'm going to have to get off the moon a little bit for this to work. But just to get a scale of things, even if we're traveling at the speed of light, it will take us a full second to get to Earth. That is the speed of light right there. Still a perceptible change, just so you all are aware. The speed of light, the fastest anything can go in the universe, it still takes you a minute to get to the moon. But how about the sun? So we are now traveling at the speed of light, very fast. We're actually slightly above the speed of light. Let's go slightly below the speed of light, just so we're traveling at still something. that actually exists in the real world. So in the real world, this is just about as fast as anything can go. In fact, if you yourself wanted to travel the speed of light, you could not do it. The closest you can get is just under the speed of light, because in order to actually reach the speed of light, you'd have to use up infinite energy and become massless, which is just a consequence of Einstein's theory of relativity. But okay, we're going the fastest anything in the universe can go. Surely it wouldn't take that long to get to the sun, right? Let's see. We are now traveling the speed of light. Earth is now far behind us. Where is Earth, actually? I've completely lost Earth at this point. It's around here somewhere. Oh, there's Earth. There's Earth. Let's recede from Earth. We are now traveling at basically the speed of light. This is the fastest anything in the universe can go. So yeah, we're now traveling at the speed of light. And even at the speed of light, it is going to take us 8 long minutes if we want to get to the sun. Fastest thing in the universe is light. Nothing goes faster than it. Even things like gravitational waves propagate at the speed of light. So the speed of light is the universal speed limit. Anything massless actually travels at the speed of light. So that's your photons, which are basically particles of light. It's a little bit weird how things work with that. Sort of the speed of light in general. Photons are interesting because they are both a particle and a wave. It's kind of strange. That's how quantum mechanics works. Very, very odd. But yes, I will speed us up far past the speed of light, but just to make it very clear, in order to get anywhere in this game, we are going to have to travel far, far faster than the speed of light. So yeah, we are now a good bit away from Earth. This glowing blue dot over here is the Earth. As you can see, it's reflecting off a lot of light from the sun. The moon is right next to it. But we're about a light minute away from Earth now. I think I've been holding my W key down for that long. But if we want to get to the sun, it's going to be 8 minutes of that. So we are going to have to speed up. So here we are now, 8 times the speed of light. At this speed, it'll take us about 60 seconds to get to the sun. So even at 8 times the speed of light, we are still barely making a dent in the universe. But now we can look a little bit around the solar system. We can see Mercury over here. Mercury is the most innermost planet of the sun. I believe it orbits the sun in about 90 days. But we are well on our way passing Mercury now, on the way to the sun, our local star. So yeah. People want me to go find life in the solar system. Or the universe. I could do that, but I want to talk about some physics first, because this is what I'm nerdy about. So, we've arrived at the sun. The sun is incredibly hot. We are now going 20 times the speed of light in this frame here, so we're going immensely faster than the speed of light already. This is just so I can show off, like, just the absurdity of how large space is, that you have to go multiples of the speed of light to even get anywhere in a reasonable amount of time. But here's the sun. I think I can just straight up land on the surface of the sun. In real life, you would be dead long before you could ever reach the surface of the sun, but here we are, sure. The sun is very interesting. The surface of the sun is 5,000 degrees. Immensely hot, insanely hot. But a weird mystery about the sun is the sun's surface is 5,000 degrees, but the sun's atmosphere actually gets up to 1,000,000 degrees. And this is something we actually haven't quite figured out yet. We don't know why. It's called the solar corona. So an idea of the solar corona is, like, if you see an eclipse, you see like the ring of fire around the moon during an eclipse. That's solar corona. That's the atmosphere of the sun. And the atmosphere of the sun is millions of degrees, and the surface is 5,000 degrees. And we have no idea why it's so hot. We have some basic ideas, most of it relating to sort of how magnetic fields work and carrying of hot plasma up into the sun's upper atmosphere. But we don't actually know why the sun's surface is so much hotter. So I think what we do now is we ignore the laws of physics, we go far faster than the speed of light, and we check out the all the planets. So I am going to enable, can I turn on labels? Let's turn on markers, maybe? Maybe not markers, actually. Got to think about what looks best here. Labels. I want labels. Oh, maybe too much labels. Maybe that's too many labels. That is quite a few labels, more than we need, actually. So maybe those are off, but we'll put orbits on. That work? Yes, there we go, perfect. So, here's the solar system as it looks like with orbits. So what you're seeing here, this AU, is called an astronomical unit. At this point, it's representing how far we are away from these objects. So 1 AU is actually a distance from the sun to Earth. So actually, if I land on the sun, or get very close to the sun, and look out towards Earth, yeah, Earth should be about 1 AU away. So 1 astronomical unit is 1 distance from the sun to the Earth. It's AU is frequently used to describe any objects within the solar system and the distances to them. So yeah, let's go for a little journey here. We're going to start by flying out to Mercury's orbit, the most innermost planet. There it is, Mercury. It is a sort of barren chunk of rock, you know. It looks like the moon almost. It's very cratered. It is very, very hot. The night side of Mercury is very, very cold, actually, because it has no atmosphere to retain heat. So this side of Mercury is pretty cold. I wonder if it'll tell us the temperature. I'm looking up in the upper left right now. I actually don't think it does, unfortunately. But the surface of Mercury during the daytime is very, very hot, and at nighttime it is very, very cold. And the reason there's such a drastic difference is because Mercury does not have an atmosphere, meaning heat cannot be retained by the planet. So if you're on this side, you'd burn to death, and if you're on the other side, you'd freeze to death. But of course, you'd die long before that because Mercury has no air. In fact, we find, as we look at things like exoplanets and whatnot, that most planets close to their suns are either constantly losing their atmospheres as it gets boiled away, or are just barren rocks because things like solar wind, charged particles will batter the planet and strip away its atmosphere. So there's Mercury. Let's move on. Let's move on to Venus, the second planet from the sun. Let's zoom out here. Again, we are traveling way faster than the speed of light. In fact, our velocity is being measured in astronomical units per second. At this point, we are going so fast. But let's come up on Venus. Venus is the second planet from the sun, and Venus is actually much hotter than Mercury. Now, you might be wondering, Venus is the second planet from the sun. Why is it so much hotter? And that's because Venus has an insanely dense atmosphere. It's called a runaway greenhouse effect, meaning that on this planet, the ground is essentially supercharged because any sunlight that comes into Mercury's atmosphere gets trapped by the atmosphere. So I don't think the game does a super great job of representing Venus's surface in this, because in reality it would be it would be covered in sulfuric acid, and it would be just the most abysmal environment you can imagine. I don't think this entirely does it justice, but Venus essentially rains sulfuric acid. It's super hot. It's the hottest planet in the solar system because the atmosphere traps in so much heat and essentially boils the planet. But yeah, Venus, incredibly hot. It's the second planet from the sun. Extremely dense atmosphere. But yeah, this is kind of cool. You can kind of see like a cloud layer maybe if I hover like right around here. But anyways, Earth we started at, so I won't visit it again. It is the third planet from the sun. It is our home. So there is Earth, and we will be moving on to Mars. Again, to get a sense of scale, we are traveling way faster than the speed of light right now. So absurdly fast that it is basically incomprehensible. But we are getting around the solar system, regardless of if we're breaking the laws of physics to do it or not. Anyway, here is Mars. Mars is the red planet, of course, as many people know. It is, in fact, the fourth planet from the sun. Its surface is red. I'm trying to land on it. Again, my rendering is not great for this game. This game does render basically the whole universe, so whenever I land on something, it's going to be a little bit low poly. But here's the surface of Mars. Mars' surface gets its red color from iron, actually, which has become this sort of red rust color. Mars does have a thin atmosphere, which is made of CO2, and Mars actually does have the largest mountain in the solar system called Olympus Mons, which I will go visit right now if I can find it. Let's see if we can find it. We might have to speed up time a little bit to sort of bring it around. There's one of Mars's poles. We do think Mars has solid water on the poles, and I think this is probably Olympus Mons if I had to guess. Let me see if there's any more noticeable one. I think that's the only noticeable giant mountain I can see there. But let's rotate Mars around to see if we can find it. Yeah, I believe that is this Olympus Mons? I think this is probably Olympus Mons. If it's not, deepest apologies. Kind of hard to tell with this game, but Olympus Mons is the largest mountain in the solar system by far. It's on the night side. Okay, hold on. Let me rotate it around. Maybe I'm looking at the wrong mountain. That's not Olympus Mons. Okay, hold on. Let's see if I can actually find it. Let's see if it rotates around. Chat, where is Olympus Mons? I think somebody is saying this one. No, not this one. Not this one. Hold on. That was it? Okay. You literally already spun it, dude. Chat is furious about the lack of Olympus Mons. It's kind of hard to tell in this game. Let me look up a picture of it so I can compare on Google. This is kind of low quality. Olympus Mons. Let me give it a little bit of an image. Okay, this might help. I'm trying to like line it up so I could properly see it. Of course the moving around is a little wonky as well. Okay, we'll use this as our reference point. Hold on. I think it is on the other side, actually. Man, they all kind of... Okay, I'll show a picture of it from Google, because there's a few that actually do look like this. I just can't find whichever one is the largest one. Hold on. I'm trying to find this... I think it's maybe this feature. I'm going to pull it up here, just so I can show you all at least this image of it from Google that I'm trying to find, but it's kind of hard with the game. Anyway, this is Olympus Mons, biggest mountain in the solar system right there. Trying to line it up, having a little bit of difficulty, unfortunately. But you know, if you guys want to try out on your own, feel free to let me know. Mars has 2 moons, Phobos and Deimos. They are both sort of potato-shaped. If I put this back on Space Engine, there we go. Zoom in on one of these. These are kind of interesting. Mars has 2 little moons, very potato-shaped, very potato-shaped. Somebody's saying this is why I bring a hammer and chisel in chat. There we go. Perfect. So there's Mars. People are saying to find Ceres. I suppose we could find Ceres. Ceres is in the asteroid belt, which is in sort of this region in between Mars and Jupiter. Oh, actually, it does have Ceres highlighted, so we can go check out Ceres real quick. That's convenient. I don't have to search for it. Very nice. There we go. See if we can zoom in on Ceres. Ceres is a dwarf planet. So dwarf planets are interesting because they are essentially spheroid objects that do have the potential to crush themselves into a sphere, but they aren't able to clear their orbit, which denies them planet status. So here is Ceres. It's a very large object. As you can see, it's mostly spherical, but it unfortunately does not clear its orbit. There are asteroids in its orbit, so therefore Ceres is not considered a planet. It's instead considered a dwarf planet. Essentially, you can just think of it as like a smaller planet. Let's go to Jupiter, which is my favorite planet, actually. It is the first of the gas giants, which make up the outer solar system. Jupiter is the largest planet in the solar system. It has a lot of moons. I can't remember if it's still the most amount of moons in the solar system. I think at one point Jupiter did have the most moons, but we just keep finding more little rocks that orbit these things, so Saturn might have taken Jupiter's prize of having the most moons. But Jupiter's moons are still really cool, and we'll go over them shortly. So Jupiter is super interesting. It is a gas giant. It has the actually the fastest rotation period in the solar system out of any other planets. I believe it's about 10 hours, so a day on Jupiter is 10 hours. It could be 10 or 9. Let me fact check that real quick. Jupiter day length. I just want to make sure I get you guys the right information. 9.9 hours. Okay, so pretty much 10 hours for a day on Jupiter. There is the Great Red Spot right there. It is a massive storm in Jupiter's atmosphere that everyone likes to talk about. It's pretty fancy. Jupiter's really interesting. It has, we think it has like these massive lightning storms beneath its atmosphere, and we think its core is made of something called like metallic helium, I believe. And metallic hydrogen, which are sort of these super states of matter where hydrogen and helium are essentially condensed so much that they change the state of matter because the pressure in Jupiter is so high. But Jupiter is also really cool because its moons. So there's the Galilean moons, which are like the very well-known ones. We'll start with Io or Io, depending on how you pronounce it, which is this one right here. And it is actually covered in volcanoes, as you can see. Volcanoes and lava, just like that. We can maybe go in for a bit of a landing and see if this looks cool in the game or not. But this is really cool because you usually don't think about moons as being these like big active objects with volcanoes and lava and whatnot. But Io does have a lot of these. Somebody is saying go to Jupiter's moons Metis, M-E-T-I-S. I could do that. Sounds good. We'll check that out before we leave Jupiter. But yeah, the reason that Io or Io has this sort of volcanic activity is because of Jupiter's gravitational pull. So Jupiter is a very strong gravitational pull. This means tides. So tides on Earth is the moon pulling the oceans back and forth, essentially. It's why we have ocean waves and high tide and low tide. But on Io, which orbits Jupiter, which has a much stronger gravitational pull, Jupiter actually pulls back, and Io is constantly being sort of squished and squeezed, which does create these sort of molten outcroppings and volcanic activity on the surface of Io, which is very, very cool. What gravity can do to a world such as this. Moving out a little bit more is Europa, which is another fascinating moon. We're actually sending a probe here right now called Europa Clipper, which will check out Europa. So what you're looking at here is a big, hold on. I'm reading chat real quick. The moon name is Matesy. Okay. Gotcha. Want to make sure I'm pronouncing things correctly. Europa here is pretty cool because it has a big ice surface. So this is actually a big ice sheet covering the entire surface of Europa. And we think that underneath this ice sheet is actually a liquid water ocean that would actually have more water than all the oceans on Earth combined, which is super cool. And we are sending Europa Clipper, which is a probe, to check it out. And it should get there in 2030, so it's got a few years to go. But whenever it gets there, we will find out whether or not Europa has any sort of water, and it has water, we think, but any sort of potential for life, which is really cool. Going outwards, Ganymede should be the next one out. Yes, there it is. Ganymede is interesting because it is actually larger than the planet Mercury, which is kind of insane if you think about it. This is a moon of Jupiter, bigger than the planet Mercury. It's called a moon because it orbits Jupiter, but it is one of the largest objects in the solar system, even bigger than a planet. So Ganymede's pretty cool. I believe Ganymede also has its own magnetic field. I'm going to fact check that real quick, but I believe so. I'm going to look it up just to make sure. Yes, it is the only moon in the solar system that is thought to have generated its own magnetic field. So there's another cool fact about Ganymede. And lastly, we have Callisto, which is the fourth of the Galilean moons, named because Galileo was able to see these through his telescope when observing Jupiter. And Callisto's out here. It is the furthest out of the Galilean moons, and I believe it is one of the most cratered objects in the solar system. As evidenced here, look at all those craters. Callisto's pretty cool. We will definitely be visiting Titan when we get to Jupiter. So let's check out this this last moon of Jupiter that was requested by chat. Let's see if it is in here. Meytse. Let's see if the game has it. It probably should have it. It has pretty much everything. Let me make sure I'm spelling it right. Oh, it's M-E-T. Gotcha. I was spelling it phonetically. M-E-T. I lost it in chat. Oh no. M-E-T-I-S. Hey, there it is. Okay. It's labeled a dwarf moon. I think I just selected it. Hold on. I want to fly to it. Go to. Bring me there. There she is, as requested. Oh, it's actually in the dark side of Jupiter. Maybe we let's bring it around to the day side so we can actually see it real quick. Let's there we go. There we go. Should be in the clear now to properly observe this object here. Now that it's not dwarfed in the shadow of Jupiter. There she is. Little oblong guy. So whenever you hear about new moons being observed around things like Jupiter and Saturn, this is mainly what we're talking about. Very small, not necessarily round objects, but there's a lot of things like this out in the solar system. Click G twice to go to an object. Thank you very much. I appreciate it. All right. I think that's going to be all I cover for Jupiter. Let's head out to Saturn next. I guess it's right over here. Let's head over. Saturn's cool because it has the rings. That's what everyone knows Saturn for. It has the massive rings. A fun fact, when Saturn was discovered by Galileo, he actually called it like a planet with ears, or an object with ears, because in his telescope it looked like just a ball and then these like strange little outcroppings here. So the rings of Saturn are not solid at all. They are actually a ton of these little microparticles, which we'll be able to see if I zoom into the rings far enough, I believe. I believe the game does animate them. Ah, yes, there they are. So, yes, Saturn's rings are made up of countless tiny objects ranging from, like, the size of a grain of sand to, like, the size of a refrigerator. And Saturn's rings are full of these. So, yeah, while we're on Saturn, unless anything else you guys would like to see, I'm going to point out Titan. Let's take a good look at Saturn first. Also, I'm interested. Saturn actually has a hexagonal pole. Actually, we can see it. There it is. Saturn's pole is a hexagon, which is kind of interesting. This results from like some very advanced fluid dynamics. Just the way the gases flow around here force it into this shape, which is actually a stable shape configuration. So this is just whenever you see fancy shapes like this in space and all sorts of symmetry, it's things taking the path of least resistance, forming the most stable shape. And in this case, a hexagon is the most stable shape that a storm could form on sort of the pole of Saturn. So yeah, let's head over to Titan, which is the big star of Saturn's orbit. Saturn does have a lot of moons. Saturn has a ton of moons, but in the interest of time, I just want to show off what, in my opinion, is the coolest, which right over here is Titan. Now, Titan is super neat because this is a moon with a full atmosphere. I'm not seeing the surface right now. You can see a little bit of a haze around it, and that's because Titan has a atmosphere with a surface below it. Of course, there's a surface below it, but it's interesting that it has an atmosphere. So Titan is interesting because it has, we think, a sort of something akin to a water cycle, except it's the methane cycle. So on Titan, it actually evaporates liquid methane into the atmosphere. Some of it escapes into space actually, but some of it does rain back down. So there is sort of a methane cycle. We think there are lakes of methane, which you can't really see here. Again, the game is a little bit low quality because I'm playing with some lower quality settings. Turn off clouds and look at it from space to see the methane lakes. Oh, cool! Thank you for the tip. How do I? Oops, did not mean to do that. Let me see if I can find the atmospheres tab real quick. Clusters, nebula, planets, atmospheres. There we go. Be gone. Let me try again. Clouds maybe. Ah, there we go. There we go. We have stripped Titan bare, and now you can sort of see those methane lakes. So let's navigate up real quick to properly see them. There they are. As you can see, shimmering off the light of the clouds, the methane lakes up here. I can't remember the exact name of the crater we're going to visit, but we are actually planning on sending something. By the way, whenever I say we, I mean we as humanity, of course. Many different nations contribute to these projects, but we're actually sending something called Dragonfly to check out Titan, which is really cool. It's a like quadcopter type thing. Which is it's really sick actually. It's like a rover except it's gonna fly because Titan's atmosphere is the right composition that you can glide really easily on it. So we're gonna send this sort of helicopter, quadcopter thing to Titan to sort of check out these methane lakes, check out a few craters and whatnot. And again, we're interested to see if life is at all capable here because there's liquid, there's somewhat of an active atmosphere. So who knows? Maybe we'll find something cool. Either way, we're gonna learn more about this really awesome moon. So. That's something I think is really, really cool about Saturn is its moon Titan. So, yeah, let's go outwards. We have 2 more planets before we get into the dwarf planets. The next one we're going to look at is going to be Uranus. Now, also, I want you guys to be aware once again of the scale of things here. Again, to get to all these planets, we are traveling much, much faster than the speed of light. And also, look at how this distance has changed. These are all the inner planets in here. There's Mars, there's Earth, there's Venus, and there's Mercury. Look how far away Jupiter is, and then look how far away Saturn is. And then, as we get to the outer planets, Uranus is even farther. So, again, space is massive, and we are barely getting started. But, yeah, let's go check up on Uranus. Uranus also has its fair share of moons, but Uranus is particularly interesting because it is actually on its side. When you look at it from the orbital plane. So the green here, the green orbits you are seeing is the orbital plane, which is essentially when solar systems form, we generally think they form out of these big disks of gas that orbit the sun. So the sun is rotating here, the gas around it is orbiting like this, and then that gas in the solar system's formation will coalesce into planets. So Uranus is interesting because it's the only planet that is actually rotating perpendicular to this. Uranus is on its side, and it spins on its side. As you can see, there is the pole. If I sort of go like this, you can see that it is pole facing the orbit. It is very much knocked on its side, which is absurd. And the reason we think this is because Uranus likely was hit by a very large object early in the solar system's formation, knocking it on its side. But Uranus is another gas giant. Oops, I accidentally unpaused time there. Maybe I should slow that down a little bit. I wanted to sort of see if I could. Oh, let's not land on it. Let's let's try to get out of the atmosphere there. But I want to see if I can get these rings to rotate. Uranus does have very faint rings, as do most of the gas giants, I believe. I believe most of them have some sort of ring, but as you can see, orbiting this way as well, these are orbiting around Uranus like that, as opposed to perpendicular to the plane, I should say. But yeah, there is Uranus. Very cool. I believe it's also the coldest planet. Let me fact check that real quick. I have to make sure I know these facts off the back of my hand. I don't do a lot of most of my classes are not focused on the solar system, so I am just spitting off the fun facts. I know a lot more about things like stars and whatnot, but yes, Uranus is the coldest planet in the solar system. That leaves us with one more planet to go, and that is Neptune. Neptune, we're going to have to go even further out. It is way over here at the edge of the solar system. Let us sort of zoom in on Neptune, and there it is. Neptune is cool because not only is it the furthest out planet, but it actually has the strongest winds. So Neptune's winds are the most powerful out of any others in the solar system. You do not want to be in a windstorm on this planet. It is ridiculous how fast the winds go. Let me actually look up just the exact speed. So I'm kind of curious myself. I don't know it off the top of my head. Let's see the wind speed. Let's see. My Google is not loading quickly. There we go. 2,000 kilometers per hour wind speed on Neptune, which is just absolutely mind-boggling. So it's a very cool Neptune fact. Very cool planet. When you finish the solar system, you check out the Black Eye Galaxy. Oh, we will check out some galaxies, of course. Anyways, moving on from Neptune, let us head out to. Let's check out Pluto. We'll make Pluto our last stop. Pluto was a planet, now it's not, for the same reasons as Ceres, cannot clear its orbit. So Pluto is very interesting. It is one of the first dwarf planets to be discovered. We called it a planet for a while, but have since declassified it, or demoted, I should say, to dwarf planet because of not only its small size, but because of its inability to clear its orbit. So here's Pluto. Oh wow, hold on. I need to slow down time a lot so I can properly look at this planet. But yeah, there is Pluto. I actually don't really like this model. Let me pull up a image of Pluto that we took from New Horizons very recently. So just so you guys can get like an actual idea of what this dwarf planet looks like. Let me quickly switch over the stream. There it is. There's Pluto. Absolutely gorgeous. It is a dwarf planet, but wow, look at that. This image was taken by New Horizons, which is the only thing that we have ever sent to make it to Pluto. So cool stuff there. Very, very cool stuff there. But yeah, again, I have to emphasize, we have sent something out here. We have sent something to the edge of the solar system. And just the vast distance of this, like going twice the speed of light, it'll still take me a ridiculously long time to get anywhere near the sun. So I'm going at the speed of light. Let's do some quick math here. Speed of light from the Pluto to the sun. It takes light 8 minutes to go 1 AU. Pluto is about 40 AUs away. So if you do that math, you're looking at like something like 5 hours at the speed of light. That's just quick math in my head. That might be off a little bit. Let's do a quick Google. I'm sure Google knows the answers. Let's see how far off my estimate was. Time it takes to get Pluto at speed of light. Okay, I was about right. About 4.5 hours is what I'm seeing from Google. So there you go. 4.5 hours. I was only off by 30 minutes. But that's at the speed of light, fastest you can go in the universe, and it would take you 4 whole hours to get to Pluto. So yeah, that is the solar system. But if you think that is a big distance, just wait until we scale things up from here. So we're traveling at about 100 AUs per second. Far, far faster than the speed of light. Far faster than anything we could have possibly ever achieved, because, you know, the speed of light is the universal speed limit. And we are just barely leaving the solar system now. To get to the nearest star, we're going to have to go a lot faster. If you were traveling at the speed of light, it would take 3 years to get to Proxima Centauri, the closest thing to our solar system. In real astrophysics, I'll keep using light years, but in real astrophysics, we refer to distances in parsecs, which stands for parallax arcsecond. All it means is that if you move one arcsecond on the sky, You can sort of do some trigonometry and get a distance that way. So whenever we talk in actual astrophysics, we usually use parsecs to describe distance, but I'll use light years because it's more familiar to people, and it is sort of like a more layman's term for distance in space. Light years is the time it takes, or the distance light travels in 1 year. So if I was to slow down to the speed of light, right? Let's do that real quick. Slow down to the speed of light. Here we go. Speed of light. I'm gonna move at this speed now. If we were to move at this speed, I would have to point at a star. I can't tell where Proxima Centauri is from here, but say Proxima Centauri is out there, and I was to hold W. It would take me 3 years of me sitting here holding down the W key for me to get from our solar system to Proxima Centauri, our nearest star. 3 years at the speed of light, the fastest anything in the universe can go. So we're obviously not going to get anywhere. Also, it's like 4.2 light years. Is that the new estimate? Let me look this up. Distance to Proxima Centauri. I've always used 3 years. 4.25. You are right. 3 years is an approximate. I think it's because it's like close to pi or something. I don't know. Usually whenever I'm taking a class on astrophysics, we get within an order of magnitude basically for distances in space. So if a star is like 80 million light years away and I get my answer as like 60 million light years, that's like close enough to be considered correct. Because those vast distances, if you're like within an order of 10, then you're fine. But yeah, let's go ahead and speed away from our solar system real quick. Let's see if I can just like maybe click on some of these to see which one is Proxima Centauri. I'm gonna have to look for it actually. We're gonna have to do a search. Let's go check this out. Proxima A. Let's go to the Proxima Centauri star. Let's head over here. Here we are. So this system's interesting because it's actually a tri-system, or trinary, maybe I should say, where there are actually 3 stars here. So there's Proxima Centauri A, B, and C. Can I see the other stars real quick? Maybe is the question. Hold on. Proxima Centauri, Hold on. I wanna try and find these other stars. I actually don't know how far apart they are, or if I'm able to see it. Okay, is this it, or is that our sun? Hold on. I'm gonna start losing track of distances here. What are you? What is this little thing here? Ah, there we go. This is actually what I was looking for. Perfect. Proxima Centauri A, Proxima Centauri B. There we go. And there's sort of the barycenter of that system there. So closest stars to the sun, right there. They are really far compared to this one. I actually did not realize how far apart these were. That is pretty interesting. So there's that, and our sun is over here now at this scale. Wait, so we've solved the 3-body problem? We have not. We have not solved the 3-body problem. You know, in real life, there are 3-body systems, but for those that are unaware, the 3-body problem is a mathematics problem where if you try and like have 3 bodies orbiting each other, the math just becomes insanely difficult, and you can't really predict its long-term behavior. Just some interesting stuff there. So yeah, let's take a step back even further. We are now going 9.05 kilolight years per second, meaning every second we go 9,000 light years. So there you have it. Let's zoom out and take a look at our galaxy. Let's actually, I want to see if I can see this a little bit cleaner. I wonder if there's anything I can do, because this is a pretty pathetic Milky Way. I want to see if I can make this look a little bit cooler. Okay, do not want to turn off galaxies. If anyone knows the best settings to look at galaxies in this game, let me know, because I do want to see the Milky Way, and I do want to see if I can get it to look nice and cool, but for some reason the background is like not cooperating with me. Maybe this is a good time for me to take a quick drink break. I'm gonna go get some water because I've been talking for a while. But yeah, at this scale, things are getting pretty incomprehensible in terms of distance. It would take a long time, even at the speed of light, to get across the Milky Way galaxy. Ridiculously large. Space is absolutely massive, and the Milky Way is only one galaxy in a slew of many galaxies. Okay, labels, markers. I'm trying to figure out what I can change here in these settings to make this look cool. If anyone knows optimal settings, let me know. If not, then oh well. I suppose we can try and get a little bit of a closer look. Oh, my computer has locked up. I have to try to hit this again, maybe. Hello? Ah, there we go. There we go. Okay, let's try and see a little bit closer into the Milky Way before we go check things out too much further out. So yeah, every speck you are seeing at the scale is a completely different star. This game is pretty cool because you can go to sort of any star you want, and they're all like real places. Like, oh, or the game can crash. That works too. That works too, I guess. Let me try and load that up. Sorry, guys. We'll continue to explore the galaxy. Let's get back into the game. Hopefully that loads. Are we in? We're back in. Where are we? Oh, we're on Earth. I believe we are on Earth. Okay, we made it back to Earth. Suppose this will be cool. We'll do a quick pull out just to see how far we've come again. There's the solar system receding. I've turned off labels at this point. We can maybe turn them back on, but yeah, what you're seeing now is a bunch of stars whizzing by. We can choose any one of these if we want to. Sort of right-click it, and we can go to the object. So, Space Engine's cool because you can see a lot of different objects in space. Some of them real, some of them not. This is apparently a real star, 60 Piscicum. Terrible with pronunciations as always, but here is a star, and here are some objects orbiting it. Toward asteroid. Okay, cool. So let's check out. I guess let's check out some of these asteroids. Toward objects are objects that are super close to their sun and are actually boiling away because of the heat. So towards are pretty neat. They are cool. Look at that star. This is a very active star. It is a yellow giant, so that makes sense. It's shooting off a ton of mass here by the looks of it. And it looks like these might be Taurid Jupiters over here, if I had to guess. What are you? No, you are a hot arid terror. You are not a gas giant, but I assume you are still boiling. In fact, yes, it looks like this planet is in fact very, very hot. Interesting. So I'm curious to see how many of these objects in Space Engine are real and how many are computer generated, because at a certain point the game does computer generate objects, but I believe these are probably all real exoplanets, because they are given names. Right there. Here's a Taurid Super Jupiter. This is more of what I was looking for. Gas giant that is boiling away because of the heat around it. Very, very cool. Kind of look at these things. Look at this world. This is like a magma world. That is sick. That is really cool, actually. Check that out. It's glowing. But yeah, very, very neat stuff. We have, in fact, found what are called exoplanets. An exoplanet is any planet that just orbits another star. So these are real. The way you find these is actually from Earth. From Earth, everything looks like this, just dots. So when you look at a dot, you can't really resolve anything about it. But what we can do is we can actually pick one of these stars and we can measure its brightness. And if there is a planet that goes in front of one of these stars, its brightness will dip by just a little bit. And by using that process of tracking transits of planets is what they're called. You can see a star, a planet will go in front of it. You won't see any change from Earth, but you will see this dot get slightly dimmer. Just using this random dot as an example, but a planet will pass in front of this star, it'll get just a slight bit dimmer, and we'll be able to detect that dimming on Earth. And if you see it periodically, which means like at the same scale, or the same time scale, I should say. So you see it once every 3 days, for example, the star is getting dimmer by this exact percent. Then you know there's a planet there. It's called the transit method, and it's how we find exoplanets. We have seen a couple images of exoplanets just from direct imaging, which is where you can actually take a picture of it. But the vast majority of exoplanets is how we found them. So yeah. I think the next step I want to do before we pull out and check out maybe the large-scale universe in this game at least is, man, the game is not wanting to render the Milky Way very well, unfortunately. You can kind of see the galaxy there, I guess, but man, that is just a disappointing sight to see. The Milky Way is being done a great disjustice by this game. Maybe I can like settings. Let me see if there's anything I can do to maybe see this. Graphics. Graphic quality medium. Let's see how high we can make it. Let's try and up it to high. Let's see if we can avoid crashing our game, but give us high graphics. Can I just, is that saved? Is that how that works? Maybe. I wanna have slightly better graphic settings. Camera, graphics. Give me high graphics, yeah. Sure. I think that should be fine. Photo mode, manual, auto. Maybe try auto. Maybe just a reset to default, actually. We'll fix things. Alright, let's see if we can see the galaxy there. I'm just trying to see the Milky Way a little bit clearer, and it looks like the game is going to fight with us on it, so that's a little bit unfortunate, but I guess we can go check this out. So, man, I'm kind of upset that the game is giving me very low quality galaxy graphics right now, but anyways, let's check out some cool features. This right here is called the globular cluster, which is just a bunch of stars that are all clustered together in like this bright array. So every single dot here is a different star. As you can see in the upper left-hand corner here, you can see what type of star it is. Lots and lots of different types of stars here. This is just a feature that you see out in space called globular clusters, which are pretty neat. I want to see, do any of these have planets? I think it tells you if it does. Number of planets 4, red giant. Yeah, it does. Let's find someone with like a lot of planets and see what there is to see around it. Go to object. Let's see what this has. White giant here. These planets probably aren't very habitable because they would be getting fried by radiation from the host star. But yeah, this looks to be a planet with some moons right here. What are you? You are a toward sub-Jupiter, and you have a lot of moons, it looks like. Can I see orbits? Maybe. I can see the orbits of the planets, not the moons, but cool. There is an interesting looking system. Hot arid supercarbonia. Check out this planet real quick. Hello there. What do you look like? You are a beautiful yellow. Very interesting. Alright. That's enough messing around with planets for now. What I want to show you all is a black hole. Now, black holes are really interesting, and I've been wanting to do this talk on the channel for a while, so I'm going to give it to you guys. Well, let's talk about some black hole physics for a little bit. First of all, let's find it. Sagittarius A. If I can type. Sagittarius A star. That is what we want. Take me to the black hole in the middle of our galaxy. Alright, here we are. This is a black hole. We think I'm going to turn off orbits because holy crap, that is causing a bit of lag. Okay, so black holes are super interesting. This is an example of an active black hole, which is one you can see the gas around it, but black holes in a lot of cases are completely invisible. Also, I'm forgetting those higher graphics settings because the game is lagging. Let's see if we can drop it down to medium and there we go, that's a little bit smoother. Now, black holes are super cool, in my opinion. They're also terrifying. These things defy everything we know about time and space. What you're seeing right now is the warping of light, because black holes are so powerful that they, for one, distort light. I mean, technically all mass does distort light, but black holes do it to a very noticeable extent. And the reason they do this is because their gravity is so high that they physically bend light. The reason they're called black holes is because if a light beam were to fall into a black hole and get sucked in by it, you could be traveling the speed of light and you could knock it out of a black hole. In fact, that is how black holes are defined. It is a region of space that the escape velocity is the speed of light or higher. So if you're on the quote-unquote surface of a black hole, which doesn't really have a surface, but if you're on the quote-unquote surface of a black hole or within the event horizon of a black hole and tried to escape by traveling upwards at the speed of light, you could not do it. You are, once you enter a black hole's event horizon, which is sort of defined as the sort of last point at which you can still escape, you will be sucked into the black hole and you will be trapped there forever. You will not be able to get out. There's nothing you can do. Now, what makes a black hole so special? Where do these things come from? So, black holes come from collapsing massive stars. So you have a supergiant, you have something that's usually they're about 3 times the mass of our sun. So any star bigger than 3 times the mass of our sun, most of the time will form a black hole when it dies. So stars have this process called fusion, which is how they produce our energy. In our sun is fusing hydrogen into helium, and the reason that happens is because temperatures are so high at the center of the sun and the pressures are so great that hydrogen atoms will combine to form helium atoms. And this process releases a ton of energy, which can power the star, essentially. Now you can think of stars as being in this sort of tug of war between gravity and the energy they are outputting. So picture it like this. You have a rope. Your friend, Mr. Gravity, is on one end of the rope, and you are on the other end of the rope, and you are Mr. Fusion. The fusion provides energy to stop the star from collapsing. It can resist gravity because the star is outputting all this energy, and this stops gravity from crushing the star into nothingness. Gravity always wants to collapse things. It wants to push things together. The reason that the Earth does not collapse into a black hole is because you push down on the ground and the ground can push back. Gravity is not super strong on Earth, comparatively, so if you step on the ground is able to push back and provide resistance against gravity. Now, the sun's made of gas. And at the center of the sun, it is a bunch of gas that's compressed super, super tightly, so tightly that it forms new elements. And that process does provide a pressure. So the center of the sun can withstand the collapse of gravity. Gravity cannot crush the sun into a black hole for some time. As the sun gets older and older, it can reach, I think our sun's going to be about 10 billion years old when it eventually dies, but you know, the sun can't burn hydrogen into helium forever. So the sun will go on its merry way, using its massive gravity and massive heat to convert all the hydrogen in the star into helium. What happens after that? Well, there's still fusion going on. You actually fuse helium into heavier elements. And this will continue for some time until you get to a point where you're having reactions that you have elements that are too heavy to release energy. Now, once you have elements that take energy to fuse together, remember, if you combine hydrogen into helium, that process releases energy. But if you have a process where you're fusing these elements together and it takes energy, you have to put in energy to do it, then the star's not putting out any more energy. And if we're using our tug-of-war metaphor, Mr. Gravity gets the upper hand and he pulls. Now, what happens when he pulls is fusion no longer works. There's no more fusion in the sun at this point. This is like 3 billion years from now, so we ourselves won't have to worry about it. But at this point, whenever the sun can no longer burn hydrogen into helium or helium into heavier elements and is instead putting in energy, the star collapses. Gravity wins the tug-of-war and pulls everything in. In our sun, we will luckily be saved by something called electron degeneracy pressure. Now, without getting into a ton of quantum mechanics here, what that means is that you take two atoms, right? Atoms are made up of a nucleus and electrons orbiting it. So maybe actually I should draw a picture for this. We're getting into a lot of more things that I can't quite use metaphors for. So I'm going to actually open a Paint document. Never get me talking about physics, because I will do this forever. So here's your atom, right? Let's have the nucleus here, which is just protons and neutrons, and you have electrons going around the outside. So electrons out here. The center is positively charged because protons. The outside is negatively charged because electrons. So when the sun gets to this point, it wants to squeeze these atoms super, super close together, but it can't, because these electrons don't want to merge, essentially. There's something called the Pauli exclusion principle. You can look it up. Essentially, electrons don't want to touch each other. They don't want to get near each other. They don't want to occupy these same orbits, give or take, is a way to describe it. So, this is a new equilibrium, and this is the ultimate fate of the sun. It is called a white dwarf, which actually, before we get to the black hole, let's go find a white dwarf. Let me see if I can just search white dwarf. Can I just do this? Object not found, white dwarf. Okay. Can I search by object? Maybe let me Google famous white dwarfs. So I could find one. Sure, list of white dwarfs. Let's just see if we can pull up one of these. Let's try Von Monden 2. There we go. Let's find a white dwarf. Okay. I wanted to go to that object. Hold on. Go to. Here we are, a white dwarf. Now, these objects are immense. This object is about the size of the Earth. If I was able to put Earth right next to it, maybe this is something for when we play Universe Sandbox, because we can do this. So here's a white dwarf. There you have it. This thing is the size of Earth. Do Control F3 to search for white dwarfs? Gotcha. I'll keep that in mind for whenever we look for the next object. So here's a white dwarf. This is what the sun will become in billions of years from now. This is where the process I just described has happened, where gravity wins, fusion no longer operates, and the star crushes itself until the atoms themselves don't want to go together. Now, you have a new tug-of-war. On one side, you have gravity trying to collapse the star, and on the other side, you have electron degeneracy pressure, which is the atoms not wanting to go together. And they are balanced. Neither one of them can win over the other, so you have this stability, and you get yourself a white dwarf. Now, white dwarfs will exist like this for billions and billions of years until they cool down. And the end state of these is called a black dwarf. We actually don't think any exist yet. The reason for that is it would take so incredibly long for this star to lose all of its energy and become a black dwarf. But a black dwarf would essentially just be the same thing except dark. Because this does have energy associated with it. It is radiating out energy in the form of heat. This is still very, very hot. Even though it is a lot smaller and a lot dimmer than the star it once was. But this will eventually radiate away all its heat and you'll be left with a black dwarf, but we don't think that the universe has existed long enough for this to happen yet. So just a quick view into like how long it would take for a white dwarf to fully die. Now you might be asking, can you get an object large enough? Can you get an object that has enough gravity so that gravity wins the tug of war with the electron degeneracy pressure? And you can, and that is called a neutron star. So let's do a Control F3, see if this works. My ships. So maybe you have a different keybind. I'm not gonna lie. But let's. That's okay because I do know of a neutron star, which is the next step, which we are going to find, and that is Lich, which is the first one. I believe one of the first ones discovered. So. This right here is a neutron star, specifically a very special type of neutron star called a pulsar. Now, you might be wondering, what happens if you have something large enough that has enough gravity to compress the star past the point of a white dwarf? And that's a neutron star. So, let's go back to our scenario from before. Let's get a really, really, really powerful star. Something that has gravity so strong that it can overcome this issue before, that we had before. So, quickly to go back, we have our two atoms. Let's say gravity is really, really strong. It compresses these atoms together to the point where the electrons that are out here actually are fused to the nucleus. Gravity wants to compress the star down as far as it can, and a neutron star, it succeeds. The electrons that are orbiting the atom are crushed into the nucleus of the atom because gravity is so strong. Now this is ridiculous. This happens when you have an object that's just over 1.4 times the mass of the Sun. A very smart person named Chandrasekhar discovered this. This is essentially the limit of electron degeneracy pressure. At this point, gravity can physically crush the atoms together, which is just, if you know anything about quantum mechanics, is just insane. Immense amounts of gravity, a tiny area. This is a star that has the mass of something larger than the Sun in the area of like your local town. So this is the size of a town, like not the Earth, not a country, but this is a star that is the size of a town. Right here, this neutron star. So there is another tug of war, gravity wins, and it physically crushes the atoms together. So the protons and electrons fuse, and so this star is just a bunch of neutrons, basically. They are very, very poorly understood. These objects are super, super strange. As you can see, it actually is distorting light. The gravity is so strong that light is being pulled around this thing, but luckily we haven't quite reached the point of no return yet. But this is actually a pulsar. Which is super interesting because pulsars are what you get when you have a neutron star that spins very, very quickly. Let's see if I can actually see it doing this in the game. Maybe not. Maybe it's not advanced enough of a simulation for this, but pulsars are interesting because you can think of them almost as cosmic lighthouses. They are these super, super dense objects that are neutron stars that have these super, super powerful magnetic poles, and with these magnetic poles, they actually shoot off big beams of light. So actually, right now I'm going to look up a pulsar graphic to show you guys what this looks like, because they are super, super cool. Is Shift F3, sorry? Oh, I see. Gotcha. Let's pull up a pulsar, just a pulsar graphic video real quick, to see if I can see this. NASA stunning pulsar animation, sure. Perfect, let's see what this looks like. Ah, there we go. That is good enough for my liking. That is good enough for me. Let's pull this up real quick. So shout out NASA, I guess, for this video right here. Let's do it. Let's put it in full screen. This right here is a pulsar. So it's the neutron star, the object that we just described, where gravity beats the power of the atom and crushes the atoms together, which is just, again, absurdly powerful. But this is what it looks like. So what you have here is a object that's about the size of a small town, has all of the mass of a star crammed in this tiny area, and it is spinning very fast. And when that happens, you get insanely powerful magnetic poles that shoot these charged particles out like beams on either side. So if you're looking at one of these things from Earth, If I look up pulsar from Earth, maybe. Pulsar from Earth. It's the minions. Okay, don't want the minions. Don't want the minions. This is probably not a great way to see this, but let's go back to our game. If you were to look at a pulsar from Earth, what you would see is this repeated flash of light. It's very periodic. Neutron stars are actually great clocks because they spin very rapidly. So like every second, for example, you're seeing that big pulse of light from before, sweeping your vision. And pulsars are very cool for this reason, because you get this very accurate clock, and if anything disturbs that clock, you know there's something passing in front of it. So actually the first exoplanets ever discovered were around a pulsar, because if you're looking at a pulsar, which has these very regular signals that are being shot out of it, because again, super powerful magnetic field, spinning super fast, with these big magnetic loops spitting out these charged particles in these big beams, then you are going to have a very regular clock. And if something interferes with that clock, you know there's a planet there, you know there's a gas cloud there, or just really anything. People have actually been thinking about using these to detect gravitational waves, so neutron stars are pretty cool. Now, if you remember our metaphor of the tug of war game, and gravity pulls and wins against the power of the atom, what is stopping it at this point? There's one more thing that can hold up a star. And what holds up a star of this sort, a neutron star, is what's called neutron degeneracy pressure. So it's the same thing as before with the electrons, except now it is the neutrons, that is what the star is made out of, that do not want to merge. The neutrons are pushing against each other, they don't want to go together. But if you get a star that is larger than about 3 solar masses, you break that. And at this point, gravity wins the tug of war for the last time, and you get yourself a black hole. I say as I dramatically click the go-to button to bring us back to Sagittarius A. So, there you have it. At this point, you have gravity so powerful that nothing can stop it. Gravity wins the tug of war, and it keeps on running with the rope. It compresses, and it keeps compressing infinitely. You end up with a singularity that is super duper small, and it's actually massless. It has infinite density, no volume, and that's what the center of a black hole is. So, yeah. There you have it. That is sort of the final frontier of physics in that regard. We actually don't know what happens at the center of a black hole yet. We have math that sort of predicts it. We know it has to be an infinitely small, infinitely dense state, because gravity just keeps on compressing it forever and ever and ever. So, yeah, if you're wondering about what this is, it has no surface. It is a singularity, and what you see here is like a quote-unquote radius is just the event horizon radius. So this is the point at which you cross it, and light can no longer pass through. Or come back out, I should say. Light can pass through, but it can't escape once it crosses this event horizon. That's what an event horizon is. So black holes are really freaky, and you get into a bunch of weird things with black holes with time, because of how relativity works. Black holes will drag space with it, they'll drag time with it. There's a bunch of weird geometry associated with black holes. These things will kill you. These things will kill you really good, is the gist of it. So, yeah, that is a black hole. So that is the journey in terms of stars right there. I find it super interesting. I hope you guys do too. If you have any questions, feel free to let me know. I'm available, of course, all the time. But yeah, there's your black hole. Shift H 3 times and press G twice. What does this do? Where is it sending me? Oh, back to Earth, I suppose. There we go. There we go. Back home. Find rogue planets with life in them. I can do that. Can you see Stephenson 218 or whatever the name is? Yes, I can. That is, I believe, the largest star, if I'm correct. Let me just verify that. Stephenson 218. Let me pull this up. Is it the largest star? I'm not entirely sure, but it is a absolutely massive star. Let's go check it out. This star is legitimately gargantuan. This is one of the biggest stars we know about. I don't know if it is the biggest star. If I can type it correctly. There we go. Oh, I need to select it first. Dang, I do not have a great grip on the controls here. There it is. There we go. Largest star. One of the largest stars that we know of. Does it actually have the size of it there? Yeah, there it is, 16 times the mass of the sun. Its diameter is 19 AU across. So for comparison, if you were to put this thing in the solar system, it would extend out to like the orbit of Saturn, I think, and maybe even then some. So yeah, this thing is absolutely gargantuan, ludicrous, ludicrous. I think no, this would go out to the orbit of Uranus. I think Uranus's orbit is 19 AU. Orbit of Uranus in AU. Let me look that up. Yes, so this thing is larger than the orbit of Uranus. So if you pulled up the solar system and put it here, this would swallow everything besides Neptune in terms of just its diameter. So very massive star. This is some of the crazy things that exist out in space. This is one of those ones that when it dies, it will go supernova, gravity will win, and this will create a black hole. And quite a large black hole at that. But yeah. If black hole warps time the closer you get to it, wouldn't the singularity not exist because the time gets infinitely slower as you get closer, or no, because of relativity? So that's one of the things that is really interesting about a black hole. And I'd have to pull up like what's called, oh, the game has crashed again. It's punishing me for talking about black holes. Now, okay, when you talk about black holes, we like to use things called space-time diagrams, which is going to get really complicated real quick with math. So let me actually point you guys to a Veritasium video. If you're really interested in this stuff, but I'll do my best summary of it. There's a channel called Veritasium. Hold on, let me find this video for you guys real quick. It's called Something Strange When You Follow Einstein's Math. It's a Veritasium video. It describes what I'm about to talk about in a lot of detail. But essentially in a black hole, space-time, which is what Einstein figured out, which is just the curvature of time and space, they work together. Space-time around a black hole curves so hard inward that time and space essentially switch places, which is weird. But the singularity is not only the center of the black hole, it is the final point in time ever, if that makes sense. It's kind of difficult to explain. It's a lot of math that I don't even fully understand because it's very, very complex calculus. Veritasium, or however it's spelled, yeah, it's a great channel. But time and space in a black hole quite literally switch places because of weird geometry, and a singularity is the final point in time that could ever exist. So, does time stop at a singularity? Technically, yes. Technically, yes. It's very strange, and we still don't exactly know how it works. A lot of things regarding black holes are just big question marks in physics because, you know, in order to learn something about an object, you need to be able to see it, and you can't see a black hole. You can never see a singularity, so you can never really know what's actually going on there. So the best we can do is math. Math is sort of the key to everything in physics. If you have a mathematical model to describe something, you can figure out a lot about it. But yeah, black holes are super strange. They break everything we know about physics. You literally divide by zero in the math, which leads to infinite density, and physics does not do well with infinities. So we do not have a great grasp of what is going on there. Yeah. All right, we're gonna go into sort of like an open-ended question, or open-ended period. I'm gonna look at some things that are, just whatever people want me to look at in terms of stars, in terms of objects. If anyone has any questions, feel free to ask. Go to Alnitak and check out the Horsehead Nebula. Ooh, that is a great idea. Let's see how it looks in this game. Actually, I can show you guys something really cool that I actually took. Hold on. I'm so glad you brought this up. Here's the Horsehead Nebula. Very cool. Actually, that doesn't look as bad as I expected it. But nebulas, essentially out in space, are these big clumps of gas. Usually they're left over after a star goes supernova. So a star will go supernova. The inside of the star will collapse into like a neutron star or a black hole, like we talked about before. And all the other gas will just sort of be left around it in what's called a supernova remnant. And eventually nebulas will form in this sort of manner. So here's a Horsehead Nebula because it looks like a horse head. I'm actually interested. Let's see if this game has the Eagle Nebula. Eagle Nebula, can I search this? Go to? It should. There you go. Oh, this one's kind of hard to see, unfortunately, but this sort of does, if you look at it from the right angle, kind of resemble an eagle. This is also home to what's called the Pillars of Creation. Um, yeah, it looks bad this game. I will say it doesn't look the greatest here. The pillars of creation are interesting because they are essentially these huge columns. Let me see if I can specifically find these. Pillars of creation. Sure. There we go. Go to. Wow. Not the best look. Does not look very good in this game. But these are essentially these big regions of dust in this nebula that are actually forming stars. So the way you get a star is you have a click the period comma keys. Oh, I appreciate that. Wait, that looks so much better. I wish I knew this ages ago. Okay, thank you very much. There we go. Now we crank the exposure way up, and now you can see them. These are the pillars of creation. These big clouds of dust and gas out in space that essentially form stars. So there's something called Jean's mass, which is essentially a region of space that is a gas cloud. And when this gas cloud reaches Jean's radius and or Jean's mass, they're kind of interlinked, they will collapse. So you have a big cloud of gas. Once it reaches a certain size, it will collapse. The gravity will become strong enough for it to pull itself together, and it will pull itself together and form a star. So that is what's happening in these pillars here. Now, I'm going to show you guys something pretty cool in just a second. So just keep this in-game graphic in your mind for just a minute longer. I'm going to actually show you guys something that I took, an image I took in one of my classes I did a while ago. Let me pull this up real quick. Two images actually. I can show you guys both of them. I'm excited. I'm excited to show you guys this. Let's see if I can properly like send them to myself. I can. Let's pull this up. Yeah, there we go. I think this is the best way to see it. Let me see if I can rotate it. I might open a Paint document just so I could rotate this image. File, new, open. All right, yeah, I can totally put this image in here. Let me show you guys an image I took. Keep that in mind. Let's switch over to this scene. There she is. That is the Pillars of Creation. This is a real image of them that I took with a telescope, with a CCD camera, it is called, which is a really fancy device. But if I sort of like enhance there, that is the Pillars of Creation right there. Sort of like a side-by-side of what it looks like in the game versus real life. But yeah, that's the Pillars of Creation. This is in the Eagle Nebula. And I should actually be able to pull up another one I took. Yeah, this one actually looks a little bit cooler. I kind of like this one better. Here's another image of the exact same spot, Pillars of Creation. I had to rotate it, so let's give it a little rotation again just to see it there. But yeah, that is it. This is a real picture I took. Hopefully you guys think this is somewhat cool. But there you go. There is the Pillars of Creation, a spot where stars are consistently being born. So there you go. There you go. Hopefully you guys think that is as cool as I think it is. But yeah, perfect. Let's peek. Take some stack exposure and false coloring. I actually did that for not this object though. The night we wanted to do this object, it was actually cloudy. So we didn't have the time, or it became cloudy, so we didn't quite have the time to take color images of this. We wanted to though. What I do have a color image of is the Triangulum Galaxy, which can be seen from Earth. Let's actually go there. Triangulum Galaxy. Click select, please. Go to. There we go. There it is. The exposure is kind of interesting. Let me lower the exposure a little bit. So that's how you see galaxies, I guess. But here it is in game. I'm going to send this picture to myself again from my phone because this one is one I actually have a picture of as well. And that one I did do the false coloring for. So I'll show the picture and I'll explain how false coloring works. Why don't we? That sounds like a cool thing to talk about. Here we go. Pull this up, send this over to myself. So here's what it looks like in game. And I'm about to show you what it looks like in real life from a telescope. So any second now it'll send. For now, just feast your eyes upon the in-game Triangulum Galaxy. But I'm just gonna throw this in Paint again, just like I did with the Pillars of Creation. There we go. That is a good picture. Here is one I took and did do the false color process for. So if we go back to this scene here, there you have it. So here's the Triangulum Galaxy. This is what it looks like from a CCD. Now a CCD camera is not like your phone camera exactly. What it does is it takes individual photons and does it sort of like, it looks black and white when you see it. But you can actually take it in different filters. So this was actually made of, I want to say like 40 or so pictures that we took of the galaxy. So what you do is you take a bunch of pictures of the galaxy in different filters. There's a red filter, there's a green filter, and there's a blue filter. And you essentially overlay these filters on top of each other to sort of get this color image of the galaxy. And that's how a lot of photos you see are done, because if you just use the detector or the camera, because of the way the camera works, it only gets photons. So the original images are all in black and white, and you color them using sort of this false color schematic. And you get really cool pictures that look like this, that sort of highlight what the stars look like and all that. But yeah, excellent stuff. Charge whatever device, right? Yes, charged coupled device, or maybe coupling. I think it's charge coupled device. Yes, it is, CCD. I actually, this is getting into more of like what I'm interested in, which I guarantee like nobody else will be, because it's super nerdy. But I'm big into cameras. I do a lot of camera work. So I know a lot about CCDs. The newer ones are called CMOS detectors, CMOS. And those ones are also used a lot for science. So whenever NASA sends something up, they're usually using a CCD or a CMOS camera. And those can be like they can be used for any wavelength. They can be used for X-rays if you want to have an X-ray camera, infrared if you want to have an infrared camera, like James Webb Space Telescope, for example. But a lot of them use CCDs and CMOS. I'm actually curious to know what JWST has. JWST detector type. I'm actually curious to what it uses. I'm curious to see if it's a CMOS or CCD detector or something else entirely, because there are more detectors. Okay. JWST uses a mercury cadmium telluride telescope, which is another type of detector. So no CCD. Does Hubble use a CCD? I'm curious. Maybe. Hubble detector type. I'm so curious to know if the Hubble uses a CCD. I want to know. Yes, it does. Okay, exactly. So Hubble Space Telescope, great example of a great telescope that uses CCD detectors to take pictures. I was pretty certain that Hubble was. I just had to confirm. But yeah, I know a lot about detectors. I'm nerdy with it. I love cameras, bro. They're so cool, dude. They're so cool. That's the future. That's how you get better images. That's how you get better stuff. Yes. All right. Give me one moment to answer a message I just got, and then I'll be right back. All right, I'm back. Sorry about that, guys. But yeah, cameras are super cool. That's the future. That's how you check out the black blob of Bernard 68. Ooh, I could do that totally. Find rogue planets with life and land on them. I could potentially do that as well. We could check it out. I'll have to remember exactly how to do those search parameters, but yeah. No. Space is cool, and things like just space agencies are cool because they have to develop technology to do more cool space stuff. So when you have any sort of space mission, you first have to build like really powerful cameras and newer cameras to do the science in question. So that's why I think detectors are so cool, and you can get really nuanced with it. There's all these different types of detectors that all do super cool things that are good for certain things out in space. But yeah, let's check out Bernard 68, and then let's see if we can find any planets with life. Barnard 68. These will be, I think, the last things I do today, because I do have some other things I need to attend to. But if you guys like this, we could totally do more Space Engine streams. All right, here it is. The black void. Look at that. Very interesting nebula of pure darkness here. I want to see what this looks like if I turn up the exposure like ridiculously high. Oh, I guess I can only go that high on exposure, but there it is. Dark void nebula. Very spooky. Very, very spooky. Alright. Now, I think if I remember, I can find... I think the command was Shift F3. Let's see if we can do it this way. Yes, this is what I want. Filter settings. Okay, I think we can do organic life, multicellular, any biome. Exotic life doesn't matter. Systems main star doesn't matter. Object parameters. I want it to be a planet. Or can I just do this? Okay, search. Go to. And I think you can find planets with life. Yes, so here's a star with 17 planets, one with life. Let's turn down our exposure a little bit. There we go. I think once we find something with life, that's when we'll call it a day. Oh, where is the planet with life? I swear it was just here, but I'm looking over here and I've missed it. All right. You see the anything, right? Let me double check that. Filter settings. Do temp marine terra. Okay. Oh, I see. Temperate marine terra. I did this once before, but I forget how. There we go. Okay. Okay. No systems. Unfortunate. Click F2 to see the planets. Can I do it from this menu? There we go. Okay, this is the one with life then. What does this have? Frigid air super aquare. Let me before we do this, because this one's currently not developing anything or showing everything. Let's see this planet right here and see if there's life on it, or like see if it's something that's like good life, you know, because there's some that are just like microbial. What do you have? Do you have life? Do you have life on you? Number of moons, one with life. So one of these moons has life. Which one of you has life? Which one of you moons? Can I hit F2 again? Ah, yes I can. Maybe. No, here it is. How do I view moons? Top left search to 1000. Check G twice to go to it. Okay. I said rogue planets. I don't know if I'd be able to search by rogue planets. And if I did, I don't know if they'd have life, because rogue planets are rogue planets are planets that have been chucked out of their solar system, so they're just free floating through space. We could try, I suppose, but I don't know if the game can account for that. Top left of the search, go to 1000. Oh, I see now. It's here. 1000 light years. Search. Okay, these no longer have life. What happened to that? Okay. Oh, it's still finding them. Okay, wait, this one has 4 with life. Hold on. I want you. Go to. Here we go. There's the star. F2 for planets. Ah, here we go. This is what we want. Do you have life? Oh, this is exactly what we want. There we go. There's the planet with life. Unfortunately, these planets are auto-generated, so there's no planets that have life that we know of outside of the solar system. This is very pretty, though. I think it's cool that the game can generate worlds like this, but there you have it. This is an Earth-like planet, I suppose. It also has what looks like an Earth-like moon. Interesting. Okay. So here's our Earth analog today. Land? Okay, let's land. Let's see what it looks like on the surface. My graphics might not be able to comprehend anything once we get there, but it's kind of a cool looking mountain. It's giving like Japan vibes. Ooh, that's pretty. We have grass. We have some sort of grass here. Oh, and there's a moon in the sky. That looks pretty neat. And like a Mount Fiji all planet. Looks like Kerbin. Catch the reference? Yes, Kerbal Space Program. Very cool. Yes. Yeah, there you have it. There is our Terra planet with life. And I think this is probably a good spot to end off today's stream. I don't have too much time today, unfortunately, but if you guys like this, I could totally come back to this game, or we could play Universe Sandbox, which is fun because you can throw stuff at each other and blow up planets and whatnot. But yeah, thank you for indulging me for this hour and a half or so of me coming on and just talking about physics that I like. Yeah, hopefully this was a cool stream for y'all. I enjoyed talking about some physics, talking about some planets and space stuff. Frame it so the moon is above the mountain. Ooh, wait, that is a great idea. Where's the moon? Okay, there's the moon. We'll have to go on this side. Let's head over here. Hey, there we go. That's pretty perfect, right? The moon right over the mountain. Maybe we can get a little bit closer to the mountain. Well, we're kind of on the mountain right now. So maybe if I pull back a little, actually, and go like here-ish. Hey, there we go. That's kind of peak. Look at that. That's pretty cool. All right. So I think that's where I'll end things off today. That is a pretty view for sure. One more question for you, KSB guy. Is there a screenshot button of any sort? Change your FOV? Wait, how do I change my FOV? Can I zoom out? Or is that in settings? Hold on. Settings. Sharpness, brightness, back, continue. I know I can save this location. Let me add this as a saved location, actually. As you can see, this is me trying to find some other stuff. Add this location. There we go. Mountain moonrise, perchance. Let's add that. There we go, perfect. Beautiful. Bottom left, click the camera button. Aha. Change FOV. Target resolution, image format. Start recording. Can I just do one? Oh, what is happening? Wait, this is bizarre. I didn't quite like that. Let me just do a oh, F1 does not work for what I want. Let's just do a regular screenshot. I can do a regular screenshot. There we go. Perfect. Let's say that's to pictures. Space engine cool planet. Why not? Why not? I'll figure out that camera stuff later. For now, I think I will see you all later. Thank you all for attending the stream. I'll leave the stream up and running for a little bit longer. But I will figure out the high resolution stuff some other time, I believe. Because I have a date with some hot wings and whatnot. But yeah. I think that's good. FOV is holding shift and left click and dragging. Wait. Oh. Maybe bring that a little bit back in, but that's kind of cool. I didn't know you could do that. Cool. Alright, and with that, I will see you all next time. If you guys thought this was cool, let me know. I'd be happy to play more of this game. I do love Space Engine. It's a really cool game. So hopefully you all enjoyed it as much as I did. I think I will see you all next time. So yeah, I will see you guys later. Goodbye.